Okay, so let's talk about quantum mechanics. It is, without a doubt, the most successful scientific theory in all of history. I mean, it predicts how atoms and particles behave with a precision that is just mind-boggling. And yet, hiding right at its very heart is a paradox so deep it makes you question the nature of reality itself. And that's the mystery we're going to dig into today, the quantum measurement problem.
So here's the conflict, right in a nutshell. Quantum theory gives us two completely different rules for how the universe works. Most of the time, rule number one is in charge. A particle's quantum state, described by the famous Schrödinger equation, just evolves in this perfectly smooth, predictable way. No surprises. But the moment you try to look at it, the second you try to measure it, everything changes. Suddenly, rule number two takes over. The system just jumps, totally unpredictably and randomly, to a single, definite state. So, what's going on?
And that contradiction is what physicists call the quantum measurement problem. It's this huge puzzle of how and why the simple act of us observing something seems to force reality to, make a choice. It turns the very act of looking into one of the central mysteries of physics and totally challenges the idea that we're just passive observers of the universe. To really get this, we've got to talk about superposition. Before you measure it, a quantum particle exists in this haze of possibilities. Think about a spinning coin. While it's in the air, it's not really heads or tails, right? It's kind of in a superposition of both. It's only when it lands, when it gets measured, that it has to pick one definite state. Well, quantum particles do this all the time. An electron can literally be in multiple places at once, until the moment we detect it. Erwin Schrödinger's famous thought experiment takes this super weird quantum rule and scales it up to our everyday world with pretty terrifying results. So you've got a cat in a box with a radioactive atom. Now, if that atom decays, which is a quantum event, so it's in a superposition, it triggers the release of poison. Since the atom is in a superposition of decayed and not decayed, the cat's fate gets all tangled up with it. And that means the cat is now in a superposition of being both alive and dead at the exact same time. It's only when we open the box to measure the system that reality seems to collapse into just one state. The cat is either alive or it's dead. So this leads us to some absolutely huge questions. Like, what even is a measurement really? Is it a Geiger counter? Is it a human eyeball? Does a conscious person have to be involved? And why do we only ever see a single dead or alive cat and not some blurry alive and dead cat? Plus, how does the math of quantum probabilities, what physicists call the Born rule, predict the odds of each outcome so perfectly? I mean, ultimately, it's all about this quantum to classical transition. How does our familiar, solid world pop out of this bizarre, fuzzy quantum foundation? For a really long time, the standard answer to all these questions was what's called the Copenhagen interpretation, developed by the pioneers themselves, people like Niels Bohr and Werner Heisenberg. It's, let's call it a pragmatic solution, but for a lot of people, a deeply unsatisfying one. So the core idea here is that you just draw a line in the sand. On one side, you have the quantum system, and it's governed by all those fuzzy rules of superposition. On the other side, you have the classical world. That's our lab equipment, our notebooks, us, which is solid and definite. A measurement is just what happens when something crosses that line. The theory doesn't even try to explain how the collapse happens. It just says, hey, it does. It's basically a shut up and calculate approach.
But a lot of physicists, including the brilliant John Bell, found this completely unacceptable. And this quote from him just nails the problem. Bell argued that measurement shouldn't be some kind of magical, undefined process. I mean, our measuring devices are made of atoms too. They should also obey quantum mechanics. You can't just have two different sets of rules without explaining why.
And, this is not a new debate. These questions have been baked into quantum theory from the very beginning. Experiments way back in 1922 showed that measurements give these definite, discrete answers. By the mid-20s, that core conflict between the two rules was already formalized. And by 1935, thought experiments like Schrödinger's cat were already showing just how deeply strange the implications really were. Okay, so this frustration with the whole Copenhagen view led physicists to propose some truly mind-bending alternatives. Instead of just accepting the paradox, they tried to solve it by completely rethinking what reality is. So let's take a little tour of some of these alternate realities. The first, and probably the most famous alternative, is the many worlds interpretation. And it offers a really radical and, in a way, elegant solution. Just get rid of rule number two. Completely. The central claim of many worlds is actually pretty simple. The wave function never collapses. Ever. When faced with a quantum choice, the universe doesn't pick one outcome. No, instead, it branches. All possible outcomes happen, each in its own separate parallel universe. So in the Schrödinger's cat experiment, the universe just splits in two. In one universe, the atom decays and the cat dies. But in another, parallel universe, the atom doesn't decay and the cat lives. So there's a version of you that sees a live cat and another version of you that sees a dead one. From your perspective, since you're trapped in a single branch, the outcome feels totally random. But from a kind of God's eye view, nothing random ever happened. Now, the trade-off for this elegant solution? Well, you have to accept the existence of a nearly infinite number of parallel realities. All right, now for a completely different approach. What if the problem isn't the rules, but the fact that we just don't have all the information? This is the core idea behind what are called hidden variable theories. So these theories suggest that the randomness we see in quantum mechanics isn't actually fundamental. It's just a result of our own ignorance. Kind of like flipping a regular coin. The outcome seems random, but if you knew the exact initial speed, the spin, the air currents, you could predict it perfectly. Hidden variable theories propose that there are these extra, hidden pieces of information that actually predetermine the outcome of any quantum measurement. So in this view, the cat was never both alive and dead. The hidden variables determined its fate from the very beginning. The so-called collapse is just the moment we open the box and find out what that fate was all along. This brings back a deterministic, common-sense reality, but it comes at a staggering price. Experience has shown that if these hidden variables exist, they have to be non-local. That means they allow for instantaneous, faster-than-light connections between particles, a concept that would have made Einstein really, really uncomfortable. So we've got branching universes, we've got hidden information. Where does the physics community actually stand on all this today? Is there a frontrunner in this race to define what reality is? Well, the simple answer is no. There is absolutely no consensus. The measurement problem is still one of the biggest, most profound unsolved mysteries in all of science. Physicists are still debating these interpretations with no clear winner anywhere in sight. But experiments have given us some crucial clues. Tests of something called Bell's theorem have definitively ruled out any local hidden variable theories. You know, the common sense kind that Einstein would have really preferred. This proved like if there are hidden variables, our reality has to be fundamentally non-local, with entangled particles influencing each other instantly across huge distances. So we've narrowed down the possibilities, even if we haven't found the final answer. And this leaves us right at the very edge of physics and philosophy. The measurement problem forces us to ask, what is reality? Is it this single objective thing that we just happen to observe, or does it branch into an infinite multiverse? Or, and this might be the strangest of all, is reality something that only really comes into being when we look at it, fundamentally linked not to what is, but to what we can know? The answer? Well, it's still out there.